In this video, you will see how complex organic-inorganic hybrid materials interact with incident light. The animations are based on quantum mechanical calculations. As a prototypical system, we have chosen a zinc oxide surface with a monolayer of pyridine molecules attached to it. Pyridine rings form the organic part of this material. This molecule is very similar to a benzene ring. However, one methane group formed by a carbon and a hydrogen atom is replaced by a nitrogen atom. Carbon and hydrogen atoms are shown in gray and white respectively, whereas the nitrogen is colored blue. In its pure form, pyridine is a colorless liquid and, due to its simplicity, a basic raw material in chemistry and pharmaceutics.
On the other side, we have the inorganic component formed by a zinc oxide surface. Zinc oxide is a transparent semiconductor with a wide bandgap of about 3.3 electron volts corresponding to near ultraviolet light. It is widely used in electronic applications and it is of particular interest for optoelectronics. The zinc atoms in purple and the oxygen atoms in red build a highly regular hexagonal pattern, the so-called wurtzite structure. The bulk zinc oxide crystal exhibits desirable electronic properties, such as high electron mobilities. Our aim is to exploit these properties in the hybrid system. Now we are approaching the nonpolar 1O-1O surface of zinc oxide. When the pyridine molecules are brought to the surface, every other zinc atom forms a covalent bond to the nitrogen atom of a pyridine ring. Thus, the surface is fully and equally covered by a pyridine monolayer. The parallelly aligned pyridine rings are slightly tilted towards the zinc oxide surface.
When the system is now hit by incoming ultraviolet light, an electron can be excited to a higher energetic state, leaving behind a positive charge called a hole. The hole, illustrated by the glowing sphere, is attracted by the excited electron via the Coulomb interaction. Such an interacting pair of a hole and an electron is called an exciton. An exciton is a rather complex object. Its representation depends on both the position of the electron and the hole. That means a function of 6 coordinates is needed to describe the exciton. In order to visualize such a complex object, we fix the position of the hole at the glowing sphere and visualize an isosurface of the excitonic wave function in 3-dimensional space. In simple words, the yellow clouds display the probability of finding an electron that was excited at a hole position. As you can see, the electron distribution changes when we change the position of the hole. The probability of finding an excited electron is particularly high when the hole is close to a zinc or an oxygen atom.
To further explore this particular exciton, we now put the hole close to an oxygen atom within the inorganic part of the system. As you can see, the dominant part of the electron distribution is located at the organic pyridine rings. Because of the special separation of the positively charged hole and the negatively charged electron, we call this exciton a charge transfer exciton. Such excitons are of particular interest for light harvesting applications. Once the charges have been separated, an electrical current can be gained by guiding the positive and negative charges to the respective electrodes. This is a fundamental working principle of a solar cell.